Section: Introduction. In this section, we discuss our exploration of language model pre-training through next token prediction, particularly in the context of scaling laws. We recognize that simply increasing model parameters and data sizes has its limits due to the availability of high-quality training data. Here, we introduce Kimi k1.5, our latest multimodal language model trained using reinforcement learning, RL, aiming to find new ways to scale effectively. We focus on several key aspects of Kimi k1.5's design and training. First, we scale the context window for RL to 128,000 tokens, which enhances performance as we increase the context length. We utilize partial rollouts to improve training efficiency by reusing previous trajectories, thus saving time and resources. We identify context length as crucial for scaling RL with language models. Next, we enhance policy optimization by applying a specific formulation of RL with long context training and using a variant of online mirror descent. This is further refined through effective sampling strategies, length penalties, and data optimization. Our approach establishes a straightforward RL framework for learning with language models. By scaling context length, we enable the models to exhibit planning, reflection, and correction capabilities. This leads to strong performance without needing complex techniques like Monte Carlo tree search or value functions. Additionally, our model is trained on both text and vision data, allowing it to reason across these modalities. We implement long-to-short methods that leverage long context techniques to enhance short context models. Our long context version achieves top reasoning performance on various benchmarks, matching or exceeding results from other models. The development of Kimi k1.5 involves several stages: pre-training, standard supervised fine-tuning, long context supervised fine-tuning, and reinforcement learning. This report emphasizes RL, starting with the curation of the RL prompt set and long context fine-tuning, followed by detailed RL training strategies. We found that the quality and diversity of the RL prompt set are vital for effective reinforcement learning. A well-designed prompt set guides the model towards robust reasoning and reduces the risk of reward hacking and overfitting. We define three essential properties for a high-quality RL prompt set: diverse coverage across various disciplines, balanced difficulty levels, and accurate evaluability for objective assessment. To ensure diverse coverage, we use automatic filters to select questions that require deep reasoning and are easy to evaluate. Our dataset includes a range of problems from different fields, including STEM and general reasoning tasks, and incorporates both text-only and image text data. We also developed a tagging system to maintain balanced representation across subjects. We adopt a model-based approach to assess the difficulty of prompts, where an SFT model generates multiple answers to gauge pass rates. This helps us filter out trivial cases and explore different sampling strategies during RL training. To prevent reward hacking, we ensure that both the reasoning process and final answers can be verified accurately. We exclude questions that are too easy to guess and propose methods to identify and remove such prompts effectively. Overall, we aim to refine our verification models in future research to enhance the robustness of our RL training process. Section Summary. In this section, we introduce Kimi k1.5, a multimodal language model trained using reinforcement learning, RL, to enhance performance beyond traditional next token prediction methods, particularly by scaling context length and optimizing policy. We emphasize the importance of a diverse and well-structured RL prompt set to ensure effective training and robust reasoning capabilities across various domains. Section: Long-Caught Supervised Fine-Tuning. In this section, we focus on long-caught supervised fine-tuning. With our refined set of prompts, we use prompt engineering to create a compact yet high-quality warm-up dataset. This dataset includes verified reasoning paths for both text and image inputs. Our method is similar to rejection sampling but specifically aims to generate long-caught reasoning paths. The warm-up dataset captures essential cognitive processes that mirror human reasoning, such as planning, where we outline steps before acting, evaluation, which involves assessing intermediate steps, reflection, allowing us to reconsider our approach, and exploration, which encourages us to think about alternative solutions. By conducting a lightweight supervised fine-tuning on this dataset, we prepare the model to adopt these reasoning strategies. Consequently, the fine-tuned long-COT model shows enhanced ability to produce detailed and logically coherent responses, improving its performance on various reasoning tasks. Next, we discuss reinforcement learning and our problem setting. We have a training dataset consisting of problems and their correct answers, and our aim is to train a policy model to solve test problems accurately. In complex reasoning, linking a problem to its solution is challenging. The chain of thought, COT, method suggests using a series of intermediate steps to connect the problem and the solution. When addressing a problem, we sample thoughts auto-regressively, followed by the final answer. We denote this sampling process accordingly. To boost the model's reasoning skills, we apply planning algorithms to explore different thought processes, which helps generate better COT during inference. The key idea here is to build a search tree of thoughts based on value estimations, allowing the model to explore various thought continuations or backtrack when necessary. We define a search tree where each node represents a partial solution, consisting of the problem and a sequence of thoughts leading to that node. A critic model provides feedback to evaluate progress and identify errors in the current solution. This feedback can be a score or a language sequence. Using this feedback, the planning algorithm selects the most promising node to expand, and this process continues until we find a complete solution. We can also view planning algorithms from an algorithmic standpoint, where past search history helps determine the next search direction and provides feedback on current progress. Since both thoughts and feedback can be seen as intermediate reasoning steps represented as sequences of language tokens, we simplify our notation. We view a planning algorithm as a mapping that operates on a sequence of reasoning steps. This perspective allows us to consider generating high-quality COT without explicitly constructing a search tree. Instead, we could train a model to approximate this process, where the number of thoughts represents the computational budget typically used in planning algorithms. Recent advancements in long context windows support scalability during training and testing. If possible, this method allows the model to conduct an implicit search over the reasoning space through auto-regressive predictions. Thus, the model not only learns to solve training problems but also develops the ability to address individual problems effectively, enhancing its generalization to unseen test problems. We propose training the model to generate COT using reinforcement learning. We define a reward model that assesses the correctness of the proposed answer based on the ground truth. For verifiable problems, the reward is determined by specific criteria, while for free-form problems, we train a reward model to predict if the answer aligns with the ground truth. Given a problem, the model generates a COT and the final answer through the sampling process. We evaluate the quality of the generated COT based on its ability to lead to a correct final answer. In summary, our objective is to optimize the policy by scaling up reinforcement learning training, aiming to combine the strengths of both simple prompt-based COT and planning-augmented COT. The model will still sample language sequences during inference, avoiding the complex parallelization needed by advanced planning algorithms. However, unlike simple prompt-based methods, the model will learn essential planning skills, including error identification, backtracking, and solution refinement, by utilizing the entire set of explored thoughts as contextual information. Section Summary. In this section, we describe our approach to fine-tuning a model using a high-quality long COT warm-up dataset that captures essential cognitive processes like planning and evaluation, enhancing the model's reasoning capabilities. We also outline how we employ reinforcement learning to train the model to generate coherent reasoning paths and improve its performance on complex problems by integrating planning skills such as error identification and backtracking. Section: Policy Optimization. In this section, we apply a version of online policy mirror descent as our training algorithm. The algorithm works iteratively. At each iteration, we use our current model as a reference and optimize a policy optimization problem that includes a regularization term. This regularization is controlled by a parameter that we set. The objective has a straightforward solution, where we calculate a normalization factor based on our current model and the rewards we receive. To estimate this normalization factor, we use samples from our current policy. We find that using the average of the sampled rewards gives us good results. As the regularization parameter increases, our estimate approaches the expected reward under our current policy. We conclude our learning process by calculating the gradient of our surrogate loss. For each problem, we sample responses using our reference policy, and the gradient we compute resembles the policy gradient method, with some differences. The main distinction is that we sample from our current policy rather than using on-policy data, and we apply an L2 regularization. We sample a batch of problems and update our parameters for the next iteration, resetting the optimizer each time since the reference policy changes. We choose not to include a value network in our training, which has been used in other studies. We believe that traditional value functions for credit assignment may not fit our context well. For instance, if our model generates a partial chain of thought and has two possible next steps, one leading to the correct answer and the other containing errors, the value function would typically favor the correct step. However, exploring the erroneous step can be valuable for training, as it allows the model to learn from mistakes and improve its reasoning skills. Our goal is to encourage the model to explore various reasoning paths to enhance its problem-solving abilities, rather than just focusing on high accuracy in training. Regarding length penalties, we notice that the model tends to produce longer responses during reinforcement learning training. While this can improve performance, excessively long reasoning processes are inefficient and not preferred by humans. To tackle this, we introduce a length reward to limit the growth of response length, promoting token efficiency. We assess the lengths of sampled responses and set rewards based on their lengths, encouraging shorter responses while penalizing longer ones, especially if they are incorrect. In our initial experiments, we find that applying this length penalty can slow down training at first. To mitigate this, we plan to gradually introduce the length penalty during training, starting with standard policy optimization and then applying a constant length penalty for the remainder of the training process. Section Summary. In this section, we describe our training algorithm, which utilizes a variant of online policy mirror descent to optimize a relative entropy regularized policy, allowing us to leverage off-policy data effectively. We also introduce a length reward to mitigate excessive response lengths during training, promoting shorter, more efficient outputs while gradually incorporating this penalty to avoid initial training slowdowns. Section: Sampling Strategies. In this section, we discuss our sampling strategies. While reinforcement learning (RL) algorithms generally have good sampling properties, their training efficiency can be limited. To enhance performance, we utilize prior sampling methods. We gather training data that comes with difficulty labels, allowing us to identify easier and harder problems. Additionally, we can track the success rates of individual problems to gauge their difficulty. We propose two main sampling methods to improve training efficiency. First, in curriculum sampling, we begin with easier tasks and gradually move to more challenging ones. This approach is effective because our initial RL model may struggle with hard problems, leading to fewer correct samples and lower efficiency. By leveraging the difficulty labels in our data, we can intuitively enhance training. Second, we implement prioritized sampling, which focuses on problems where the model performs poorly. We monitor the success rates for each problem and sample them based on their failure rates. This means that problems with lower success rates are sampled more frequently, directing the model's learning efforts toward its weaknesses. For coding problems, we face the challenge of generating test cases since many are not available online. We developed a method to automatically create test cases that serve as rewards for training our model. We focus on problems that do not need a special judge and assume we have ground truth solutions to generate high-quality test cases. Using the k1.5 library, we generate 50 test cases for each problem and sample 10 ground truth submissions. A test case is valid if at least 7 out of 10 submissions match. We include a problem in our training set if at least 9 out of 10 submissions pass all selected test cases. From 1,000 online contest problems, we found that about 614 do not require a special judge, and we created 463 test case generators, resulting in 323 problems added to our training set. In terms of reward modeling for math, we recognize that different written forms can represent the same answer. To improve our reward model's accuracy, we adopted 2 methods. The first, classic ERM, is inspired by the Instruct GPT methodology, where we collected around 800,000 data points for fine-tuning. This model evaluates the input question, reference answer, and response to provide a correctness score. The second method, chain of thought ERM, uses a step-by-step reasoning process to enhance scoring accuracy, particularly for nuanced tasks like math. We also collected about 800,000 examples for this approach. Our evaluations showed that classic ERM achieved an accuracy of approximately 84.4%, while chain of thought ERM reached 98.5%. We chose to use chain of thought ERM during RL training for more accurate feedback. To enhance our model's image reasoning capabilities, we sourced our vision reinforcement learning data from 3 categories: real-world data, synthetic visual reasoning data, and text-rendered data. Real-world data includes various science questions requiring graphical understanding, location guessing tasks, and data analysis involving complex charts. Synthetic data consists of procedurally generated images aimed at improving specific visual reasoning skills. Text-rendered data converts textual content into visual formats, ensuring consistency in responses across different input types. Each data type is crucial for building a robust visual language model that can handle diverse real-world applications effectively. Section Summary. In this section, we explore improved sampling strategies for reinforcement learning, RL, by implementing curriculum and prioritized sampling methods that focus on problem difficulty and model weaknesses, respectively. Additionally, we discuss our approach to generating test cases for coding problems and enhancing reward modeling for math solutions, ultimately aiming to improve the model's performance and real-world reasoning capabilities through diverse vision data sources. Section: Evaluation. In this section, we evaluate the Kimi k1.5 multi-modal model across various benchmarks for different modalities. The detailed evaluation setup is available in the appendix. For the k1.5 long-COT model, we present its performance in a table. We enhance the model's long-term reasoning abilities through long-COT supervised fine-tuning and vision text joint reinforcement learning. The scaling of computation during testing further boosts its performance, allowing it to achieve top results across multiple modalities. Our evaluation shows significant improvements in the model's ability to reason, understand, and synthesize information over longer contexts, marking a step forward in multimodal AI capabilities. Regarding the k1.5 short COT model, we also present its performance in a table. This model combines several techniques, including traditional supervised fine-tuning, reinforcement learning, and long-to-short distillation. The results indicate that the k1.5 short COT model performs competitively or even better than leading open-source and proprietary models across various tasks, excelling in natural language understanding, mathematics, coding, and logical reasoning. For long context scaling, we use a mid-sized model to explore the scaling properties of reinforcement learning with large language models. We illustrate the changes in training accuracy and response length over iterations for a smaller model trained on mathematical prompts. As training progresses, we notice that both response length and performance accuracy increase together. More challenging benchmarks lead to a sharper rise in response length, indicating that the model learns to produce more detailed solutions for complex problems. Our findings show a strong link between the length of the model's output context and its problem-solving abilities. In our final run, The k1.5 model scales to a context length of 128,000 and continues to improve on difficult reasoning benchmarks.